Hello and welcome to your bonus multiple choice review video for Chapter 7, where we discuss sampling distributions for sample means and sample proportions. The first toss-up here is a study of voting chooses 663 registered voters at random shortly after an election. Of these, 72% said they had voted in the election. Election records show that only 56% of the registered voters voted in the election. So we have some liars here. Which of the following statements is true about the bold-faced numbers? So which numbers are we really saying are the bold-faced numbers? Well, that would be our 56% and our 72%. Now, what do these numbers represent? Well, the 72% relates to the 663 registered voters chosen at random. So the 72% is a sample statistic. So 72% is a sample. Well, not quite. It's a sample statistic. 72% and 56%, we'll talk about this first. 72% is a statistic. So far this is okay. It's okay with the 72. 72% is a statistic. Sounds good so far. 72% is a parameter. Well, parameter is related to the population, so this doesn't quite match up. And 72% is mentioned as a parameter, which again is incorrect. Now, when it says the election records show that only 56% actually voted in the election, they are referring to the whole population that voted. So the 56% is a population parameter. So part A, again, they've got the first word here, but they really need to follow it up with parameter to make it correct. So the way it stands, it's not technically right. In part B, 56% they said is a statistic, but that's really not true. We said it's a parameter, which means answer choice C is our only viable option. Number 2, the Gallup poll has decided to increase the size of its random sample of voters from about 1,500 people to about 4,000 people right before an election. The poll is designed to estimate the proportion of voters who favor a new law banning smoking in public buildings. The effect of this increase is to reduce the bias of the estimate, increase the bias of the estimate, reduce the variability of the estimate, increase the variability of the estimate, or E has no effect since the population size is the same. Well, to be honest, the whole bias effect here really has nothing to do with the size of the population. If you do not take care of getting your sample, essentially, if it's not random, if it's not done properly, if it's convenient sample or based on voluntary response, you can't get rid of that bias, no matter how many times larger your sample is. So A and B are just wrong altogether. We cannot reduce bias. We can't increase bias by increasing our sample size here. The sample size really has more to do with our variability. Okay. Now, the variability, essentially what we're referring to here is the spread, how much variation there is. And if we increase our sample size, then we found out in our formulas for sigma sub x bar and sigma sub p hat that as we increased our sample size, that it decreased our standard deviation or our spread or our variability. So the effect of the increasing of the sample size is really to decrease our variability or our standard deviation. Number 3, suppose we select a simple random sample of size 100 from a large population, having proportion P of successes. Let P hat be the proportion of successes in the sample. For which value of P would it be safe to use the normal approximation to the sampling distribution of P hat? Now, when they refer to the normal approximation, that's referring to rule of thumb number 2, that the n times P must be greater than or equal to 10, and the n times 1 minus P must be greater than or equal to 10. And they gave us one of these numbers, right? They gave us 100, the n. So really we have 100 times something must be greater than or equal to 10, and 100 times 1 minus that same something must be greater than or equal to 10. So what number would be safe? Well, I mean, we could just take our choices here and start plugging them in. If I took 1/100th of 100, that would leave me with 1, and 1 is not greater than or equal to 10, so that's not going to work. 1/11th is essentially just a smidge more than, not really, that's 1/10, 0.1. So if we plug that in, we'd have 100 over 11, and what's that going to be? Let's see. Come down here. 100 divided by 11. We get 9.09 repeating. So this is not greater than or equal to 10. 0.85. Let's see here. If we plug in 0.85, well, 100 times 0.85 would give me 85, which is greater than or equal to 10. So far, so good. And if I plugged in 0.85 over here, well, that would leave me with 0.15, and 100 times 1, or 0.15, would be 15. Oops, meant to be at 10 there. And so both of these are good. Now, it does say for which value of p would it be safe. So far, so good. We're safe here. But what do you think is going to happen? And you might think, well, since we got larger and larger and larger, it finally worked. But what would happen if we picked these very large values for p hat? You might think, well, they're going to work, right? Because 100 times 0.999, well, that's going to be 99.9. That's definitely going to work here. But these aren't going to work over here, because then we're looking at basically the complement of what we have. We would be taking 100 times 0.001, and we would definitely not get something greater than or equal to 10. So both of these are going to produce unfavorable results for the second half of rule of thumb number 2. So the only one that really works is 0.85. Number 4, the central limit theorem is important in statistics because it allows us to use the normal distribution to make inferences, or we get to apply our results to the population concerning the population mean if so if the sample size is reasonably large for any population. So can we make inferences with the central limit theorem about the population mean if the sample size is reasonably large? And this pretty much sounds like the central limit theorem. So it kind of seems odd. We'll just say, yeah, let's kind of hold on to this one. This one seems good, but let's see maybe why the others are wrong. So if the population is normally distributed and the sample size is reasonably large. Well, we got the sample size is reasonably large. That's good. But do we have to have the population already being normally distributed to use the central limit theorem? No. So that one really doesn't work out. You know, this half works, that the sample size needs to be big enough. The population doesn't have to be normal. C, if the population is normally distributed for any sample size, well, then we really don't need the central limit theorem for a sampling distribution, because the sampling distribution will naturally be approximately normal if the population is normal. So we don't even really need the central limit theorem for this. If the population is normally distributed and the population variance is known for any sample size. Again, we don't really need to know the population's normal to do this. E, if the population size is reasonably large, whether the population distribution is known or not. Again, it's not the population size that we need to be reasonably large. It needs to be the sample size that's reasonably large. So it is A, in fact, is the one that matches up here. Number 5. The number of undergraduates at Johns Hopkins University is approximately 2,000, while the number at Ohio State University is approximately 40,000. At both schools, a simple random sample of about 3% of the undergraduates is taken. Each sample is used to estimate the proportion P of all students at that university who own an iPod. Suppose that, in fact, it's 80% at both schools. Which of the following is the best conclusion? So the estimate at Johns Hopkins has less variability than Ohio State, or Johns Hopkins has more variability than Ohio State, or the two estimates are about the same, or it's impossible to make any statement about sampling variability of the two estimates since the students surveyed were different, or E, none of the above. Now, you might think that maybe it's the same because they sampled the same percentage, but that doesn't relate to our sample size, which is key here. And since we're talking about variability and we're talking about proportions, we need to think about our formula of sigma sub p hat, which is p times 1 minus p over n. Now, they did tell us what p was, that p was 80%. So both formulas, if we said this was sigma sub p hat sub JHU for Johns Hopkins University, we would use 0.8 in both of these cases versus sigma sub p hat sub O8, or not OH, what am I thinking? I don't want to spell Ohio, OSU, and we'd have the square root of, and again, it would still use the same 0.8s, but we would need to know the sample size. So to get the sample size, we need to take 3% of our 40,000 and 3% of our 2,000. Now, if we want to kind of look at Johns Hopkins here, its sample size, or 3% of 2,000, well, that would be, 60 would be the sample size? And 3% of our 40,000 would be, 1,200. Now, we talked about that if basically our numerators here underneath our square roots are the same, we have a much larger sample size for Ohio State, which means its sampling distribution standard deviation is going to be much less than Johns Hopkins, which means Johns Hopkins has more variability. It's spread out more. So we would want B, the estimate from Johns Hopkins, has more sampling variability than that of Ohio State because it has a smaller sample size, and Ohio State has more. So let's just check to make sure. B is the answer. Number 6, a researcher initially plans to take a simple random sample of size n from a population that has a mean of 80 and a standard deviation 20. If he were to double his sample size to 2n, the standard deviation of the sampling distribution of the sample mean would be multiplied by what? Okay, so if we originally were looking at this would be our formula, and if my sample size, we can go ahead and plug 20 in here. We know 20 is here, but we don't know what the sample size is. They just said it was n, so I just leave it as n. Now, they want to talk about what would happen if we doubled it to 2n. Well, we'd still have 20 in the top, but in the bottom we'd have the square root of 2n. Now, they were saying that this standard deviation would be multiplied by what to get this sampling distribution standard deviation? And really the only difference is that 2 down the denominator. Now, it's not just a regular old 2, it's a square root of 2. So if we wanted to, we could do this. We could take 20 and then split up the 2 and the n into their own individual square roots. And then we can put a 1 up here and kind of make it its own separate little fraction. So here is the kind of multiplicative difference here. It's 1 divided by the square root of 2, which should give me answer choice B. Now, this E looks just about like the same thing, but that n really shouldn't belong there. Now, another thing you could do, just throwing this out here, you could make up a number for n. You could say, what if the sample size was 100, and then it went to 200? And then you can actually figure out, well, what is this? Well, let's see, that'd be 10, so that would be 2. And then this would be, 10 root 2, so 2 divided by root 2. This would be 2 root 2 over 2, which is root 2. So you could figure out 2 times x should be the square root of 2, and you can divide both sides by 2, and there's basically rationalized 1 divided by the square root of 2. So you get the same answer. So it doesn't matter what n really is here, so you can make up any number you want and actually look at the values of those standard deviations. Number 7. The student newspaper at a large university asks a simple random sample of 250 undergraduates, do you favor eliminating the carnival? Why would you want to eliminate a carnival? From the term in celebration. All in all, 150 of the 250 are in favor. Suppose that, unknown to you, 55% of all undergraduates favor eliminating the carnival. If you took a very large number of simple random samples of size 250 from this population, the sampling distribution of the sample proportion p hat would be... So here's the thing. So they want us to describe the sampling distribution, which means we need to discuss the size. Not really the O so much, but the shape, the center, the spread here. Well, let's talk some numbers here. So they're saying unknown to you, it's really 55%. That's everybody. So the 55%, 0.55, that's P. That is our population parameter. P hat is just our 150 out of 250. What else? We have a sample size. If we took sample size of 250 here, then would we know that it's exactly normal, approximately normal, heavily skewed? They really didn't tell us any idea here of the shape of the population. So we can't assume that it's normal or that it's skewed. We really have no idea. But to determine the shape, that's where we had rule of thumb number 2. And we could check, is n times p and n times 1 minus p both greater than or equal to 10? So we've got 250 times 0.55, and then 250 times basically 0.45. And so what do those come out to be? Let's grab our old calculator here. 250 times 0.55, it's 137.5. That's definitely more than 10. And times 0.45, 112.5. So both of these conditions have been met, which means we may assume, so it's definitely not heavily skewed. Now, is it exactly normal or approximately normal? We're always going to go approximately normal. Unless you were told that something is perfectly normal, we're always going to go with approximately normal. So it's not A, it's not C, it's either got to be B or D. Now, we've got the S of our socks, the first S taken care of. We said ignore the O, and let's move on to the C, the center. So we want to figure out what is mu sub p hat. And that should be our population parameter, which is 55%. This says a mean of 0.55, but this says a mean of 0.6. And where does that 0.6 come from? It's going to come from p hat, the 150 out of 200. So they picked the wrong value here. And you'll notice that both of these have the same standard deviation. So, hey, 0.03 has got to be the right standard deviation. So our answer should be B, and it is. Number 8. Which of the following statements about the sampling distribution of the sample mean is incorrect? Part A. The standard deviation of the sampling distribution will decrease as the sample size increases. So sigma sub x bar equals sigma divided by the square root of n. So it's saying that this will decrease if we increase the sample size. And that's true. Again, we're looking for the incorrect statement. So this is good. Part B, the standard deviation of the sampling distribution is a measure of the variability of the sample mean among repeated samples. And this is also true. A sampling distribution is looking at all the different possible combinations of x bar, of all these different sample means. And so the sigma sub x bar is a measure of the variability of those sample means. So this is true. C, the sample mean is an unbiased estimator of the true population mean. Now that is true because that's based on our formula. The mean of all the sample means is really equal to the population mean. And that's what it means to be an unbiased estimator, is when the mean of all your sample statistics is the same as the population parameter in general. So this is true. D, the sampling distribution shows how the sample mean will vary in repeated samples. And that's true. That basically goes back, basically goes back to our picture here. The sampling distribution does show how all our sample means in this case will vary in repeated samplings. We're not always going to get the same sample mean for every random sample we take. So this is true, which means E has got to be our answer. The sampling distribution shows how the sample is distributed around the sample mean. That really just doesn't jive. You know, they're kind of acting like the sample mean is one thing in a sampling distribution, when a sampling distribution is made up of nothing but sample means. There's multiple sample means in a sampling distribution. So this is the one, E, correct. That is the one that is incorrect overall. Number 9. A machine is designed to fill 16-ounce bottles of shampoo. When the machine is working properly, the mean amount poured into the bottles is 16.05 ounces with a standard deviation 0.1 ounce. Assume that the machine is working properly. If 4 bottles are randomly selected each hour and the number of ounces in each bottle is measured, then 95% of the observations should occur in which interval? Now, they're kind of wanting you to believe here, since they throw that 95% in here. And if you remember, once upon a time, we had this thing called the 68, 95, 99.7 rule, right? Which we also called the empirical rule. Empirical? There we go. Empirical rule. And the 95% was basically plus or minus 2 standard deviations above and below the mean. And so they're wanting us to think that we need to use a normal distribution. But what I want you to consider is this. Number 1, did they mention the shape of the population of all these shampoo bottles? And if you go back and reread it, they didn't. So then what we need to try to fall back on is, can we use the central limit theorem here? This is a mean problem, a sampling distribution of sample means of the mean amount of shampoo that's in each bottle. And so we need to hope that we have a big enough sample size for the central limit theorem to apply. But here's our sample size, 4 bottles. And that's not guaranteed to be large enough to ensure that the central limit theorem is going to apply. Which means our answer must be, we can't really compute a 95% interval that'll tell us what we have here. Now, what they want you to do is to take 16.05, the mean, and they want you to add and subtract 2 standard deviations worth, which would be 0.2 based on this. So they want you to give an answer of 15.85 up to 16.25. And are any of those possibility here? Did I do my math wrong? Did I do my math wrong? No, I didn't do my math wrong. Well, none of those really even work out anyway, so boo. I was hoping they would have had that as well as the answer choices, but they don't. Anywho, last problem. Suppose that you are a student aide in the library and agree to be paid according to the random pay system. Each week, the librarian flips a coin. If the coin comes up heads, your pay for the week is $80. If it comes up tails, your pay for the week is $40. You work for the library for 100 weeks. Suppose we choose a simple random sample of 2 weeks and calculate your average earnings X bar. The shape of the sampling distribution of X bar will be normal, approximately normal, right skewed, left skewed, symmetric, but not normal. Now, here's the thing. What shape is the population? Well, we don't really know, right? We don't know how many weeks out of the 100 weeks you got paid $80 and you got paid $40. Now, if we wanted to come up with a kind of a theoretical situation here, we could say here's $40, here's $80. So we would think if we're flipping a coin, it should be about half and half, right? Like if this was our vertical axis, we would expect 50 times out of 100 we would get paid $40, and 50 times out of 100 we'd get paid $80. Which means the shape of this distribution, this is the population in general, kind of our theoretical population, is symmetric. It is technically symmetric, right? It's also, I guess you could call bimodal, but it's kind of weird, right? So we want a sampling distribution based on a sample size of 2 weeks. So here's what we need to consider. Let's pretend that we're going to get a sampling distribution. Now, thankfully they only picked 2 here, sample size of 2. So what could be our 2 values that we get? Well, we could get 40 and 40, right? Those could be our 2 random observations for our 2 weeks. And so the mean of 40 and 40 would still be 40, right? So we'll just put a value right here at 40. Or we can go on the other end and say, well, what if the 2 weeks I picked were weeks of 80 and 80? Well, that would be true. But chances are I'm probably going to pick one of each of these, right? So what if one of my weeks was 40 and the other one was 80? Well, what's the mean of 40 and 80? Well, the mean would be 60. Now, really, I got the same. Well, think about this. How do we want to consider this now? If I picked one that was 40, then I have a little bit greater chance of picking an 80 because I've already picked a 40 and vice versa. So I would kind of think that 60 would be a little bit higher than a 40 and 80. Now, can we assume that this is normally distributed? Definitely not with a sample size of 2, but what shape is this? We can't say it's normal. We definitely can't say it's approximately normal. I mean, the central limit theorem definitely doesn't apply based on, the population being, even uniform and bimodal, symmetric. This thing's just crazy. It's not right skewed. It's not left skewed. Now, this thing is symmetric, right? Symmetric around $60, but I don't think we can safely say it's normal just because the sample size is 2 weeks. If the sample size was, say, 30 weeks, then we could say it's definitely going to be roughly symmetric and normal. So if our sample size was large enough, the central limit theorem could kick in, and then we could safely say that it is approximately normal. Really, at that point, we could just go with B, because that is approximately normal. So that is all. Good luck studying, and hopefully you rock the multiple choice part on the test.